Okay. All right, so let's go to the beginning. Okay, so everybody's seen my screen? Yes?
Hmm.
Okay,
Yep.
good, good. So we want to welcome everyone again to season 8 of
Yeah.
Environmental Fridays. It is personal. This is our 12th episode for this season. And if you want to find more details about Environmental Fridays, you could go to our web link here, website, the URL there. In the bottom right corner is this QR code that will also get you there. This is our speakers for this season 8. You could see we've gone through a lot. We are here now with Annie, and
Mhm.
we have a few more to come for this season. Um, we want to also acknowledge our partnerships. We are partnering with the American Chemical Society, ACS Committee for Minority Affairs, and we hope that will also give a greater impact to Environmental Fridays. We also partner, we have a long standing partnership, 23 years actually, with the Benton Spirit Community newspaper. Princella Tobias is the founding publisher, and she is online here. You will probably hear from her. And she was just actually recently awarded, like yesterday, awarded for her community engagement, particularly dealing with environmental awareness, dealing around the problem of lead and water pollution in the area of Benton Harbor. So she was recognized by Andrews University for that work yesterday. And we also partner with my sister. This is her organization, GC Scored, involved with social emotional learning and wellness. So, if you would like to join our Facebook group, just go to Google and put in Environmental Fridays Facebook group, and you will immediately get to our links for joining the Facebook group. Same thing with our YouTube playlist. We have the YouTube playlist for every season, seasons 1 through 8. I believe this QR code would get you to season 8, our current season. So we have come essentially to the end of March. It was started out and we've been through here like pretty quickly. Time is just flying by. And so we'll be listening to and hearing from Annie today, Dr. Kretcher, on the future of sustainable energy. You'll hear some more here soon. In the upcoming month of April, essentially for the most of the month, there will be celebrations around Earth Month, National Garden Month, Poetic Earth Month, and of course, April 22nd is Earth Day. So all you've got, if you're interested in any of these, just go online and Google them, and you'll find out a lot more information about these environmental observances. So I am pleased to have as my co-host today, Alyssa Gabrielle. It's probably about 10 years, I think, isn't it, Alyssa, that we've known each other?
Yeah, maybe more,
Maybe
Doc.
more. Yeah.
Yeah, I think it may be more, and it's been wonderful knowing
Yes.
you.
It has been. It has been great friendship, wonderful person, caring person. So I'm gonna give a formal introduction of her. She is a literary powerhouse, and that is literally true. publisher, visionary leader with over 200 books published and more than 25 literary careers launched. She is a national best-selling author, screenwriter, producer, certified master life coach. She also holds a doctor of
Hey, Sammy,
naturopathy.
you can hold on that.
Okay, we need somebody to like mute here. Who's
Just an animal. That's a total.
okay, let's mute. Okay. All right. Um, so she blends storytelling with healing, and through her expertise in natural health and wellness, she has transformed countless lives by guiding people toward holistic healing and vitality through natural modalities. I could say that she's also advised me. I don't know if I've been a faithful follower, but she has advised me dealing with health issues. Known as a midwife of greatness, she has an extraordinary gift for transforming raw talent into literary superstars. Her acclaimed The Soul of a Man series honors Black men's voices, while the You Are Enough and the Power series inspire radical self acceptance and transformation. She is a trailblazer with 30 plus literary award nominations and continues to shape narratives that ignite, elevate, and inspire. I was just going to ask you, Alyssa, in the last year, let's just say last year, last few months, what are some of the new projects, continuing projects that you've been working on? Just to share a little bit with our
You
audience.
know, with Peace in the Storm Publishing, and thank you so much for that introduction. That made me feel good, actually. So,
Okay.
uh, with Peace in the Storm Publishing, we have some wonderful children's books that are going to debut this year for some dynamic authors. We're actually celebrating our 20th anniversary this year in 2025. So I'm so happy about that for the endurance, right?
Mm-hmm.
I have a new novel coming out under Elisa Gabriel's Deja Vu.
Oh,
It's just been picked up by Recorded Books, so I'm happy about that. We released the You Are Enough series at the end of 2024, and this year I will be releasing the Power series, and that's going to start to release in June of this year. And there's so many
the
other things
Power
in
series, is
between.
this
Yeah.
a video? Is this,
It's a four-book series, and the first book is The Power of No.
oh, okay, okay.
Book two is The Power of Letting Go. So it's
Ah,
radical
okay,
self-preservation and self-care.
okay, very nice, very nice.
Mhm.
All right, so it's your turn now to introduce our speaker
Yes.
today.
Well, listen, we are so honored to have Dr. Annie Critcher with us this morning on Environmental Fridays, and I'm going to give you a formal introduction on Dr. So Dr. Annie Critcher is integrated modeling team lead in the Inertial Confinement Fusion ICF program at Lawrence Livermore National Laboratory. She designed the first experiment to achieve fusion target energy gain in any controlled fusion scheme. Annie earned her MS and PhD in nuclear engineering from the University of California, Berkeley, and her BS from the University of Michigan. She was named one of Time Magazine's 100 most influential people in the world in 2023 and one of Nature's 10 lists of people who made a significant impact in science in 2023 and is a fellow of the American Physics Society. Wow.
I
So
know.
we are so honored
Yeah.
for your time this morning, Dr. Critcher. Welcome.
Oh, thank you so much for that introduction and thank you for having me here. Should I go ahead and share my slides now?
Oh, not yet. Remember,
Okay.
we were gonna
Sorry.
we're gonna show an introductory
Right.
like
Thank you.
video. So this is it here.
This is it, Jamie. What is
Yeah,
this?
this is actually on the news
Don't
today. There
want
was a
to
briefing.
shock.
Our government just shocked every American by how.
Okay.
To present our first Genius Award, I'd like Ralph and Karen Izzo to join me on the stage. Mitty. Many of you know Ralph as the retired chairman of the board, CEO, and president of PSE&G, the power company. You may not know that he has a PhD in applied physics from Columbia and began his career as a research scientist at Princeton Plasma Labs. Karen is a biologist by training. With these backgrounds, I invite Ralph and Karen to present the first award.
So thank you, Paul. Annie Kreitzer, is a nuclear physicist and engineer at Lawrence Livermore National Laboratory in California. Dr. Kreitzer is the engineering design lead on the experiment that in December 2022 achieved the holy grail of nuclear physics, igniting the world's first controlled nuclear fusion reaction to release more energy than it consumed.
Nuclear fusion is the mechanism that powers our sun and the stars. Unlike nuclear fission, the energy generating reaction in today's nuclear power plants, there is no highly radioactive byproducts in nuclear fusion, and it is a clean source of energy. The Lawrence Livermore team went on to successfully repeat the experiment 4 times. May we have a video, please?
One day soon, man is going to be able to harness incredible energies, maybe even the atom. Energies that could ultimately hurl us to other worlds in some sort of spaceship. And the men that reach out into space will be able to find ways to feed the hungry millions of the world and to cure their diseases. They will be able to find a way to give each man hope and a common future. And those are the days worth living for. Our deserts will bloom.
Development of atomic power is years away. Space flight years after that.
Being able to harness nuclear fusion would be a breakthrough for mankind. It would change everything about the way we live. It is the holy grail of energy. It's clean, it's unlimited.
Annie Kreitzer is leading the quest for this holy grail. She's a nuclear engineer, physicist, and lead designer of fusion experiments at Lawrence Livermore National Laboratory. There she tries to recreate the same reaction that powers the sun and other stars. Intense heat and pressure can make 2 atoms fuse together into one, releasing energy. The process doesn't produce greenhouse gases like fossil fuels do, or radioactive waste like the nuclear fission or splitting reaction used in today's nuclear power plants.
The fuel source is forms of hydrogen. One of them you can find in seawater, and the other one you can find fractions with lithium. Estimates are that for one person's lifetime, you'll only need a bathtub of seawater and 1 laptop's battery worth of lithium.
Wow. But before that happens, scientists have to learn to achieve fusion ignition, getting more energy out of a fusion reaction than it takes to start it. They've been trying to do that worldwide since the 1950s. Here inside the 10-story high National Ignition Facility, they've made more than 170 attempts by bombarding a tiny fuel pellet with the world's biggest laser.
We have the biggest laser in the entire world, 450 terawatts, 1.9 megajoules, actually up to 2.29 megajoules now. Once the laser energy comes into the target chamber, it hits a target or a hollow can that's made up of gold-lined depleted uranium. The lasers actually hit the can itself. That creates an X-ray radiation bath. So an X-ray oven that's about 3 million degrees in temperature. So the X-rays heat up the outside of a pellet that sits inside of the can. It's a hollow pellet. In our case, it's made up of diamond. And then inside of that pellet is the fuel, the deuterium and tritium fuel that we're trying to fuse. The X-rays heat the outside of the pellet, and it's just like a rocket. The rocket fuel goes out, the rocket goes up. So here we expand out that pellet material outward, and that causes the rest of the material to squeeze down, and that's what causes the heating and compression, because you're taking something of a big volume and squeezing it down to a really tiny volume. The pellet is 2 millimeters roughly, so it's about the size of a BB, sitting inside of the can, which is about 1 centimeter, about the size of a pencil eraser. We take that BB-sized capsule and we squeeze and compress the plasma down to half the width of a human hair.
But after decades of work around the globe, no lab had ever achieved ignition. Kreitzer and her team kept fine-tuning thousands of parameters in their experiment.
Our job is really what are the optimal target conditions and laser conditions to create the right plasma physics, to get the plasma hot enough and dense enough and confine it for long enough, because we need to create star-like conditions to actually generate more fusion energy out than what we put in.
And on December 5th, 2022, they succeeded.
The first breakthrough experiment was 5 times hotter than the center of the sun, actually more than that.
5 times hotter than the center of the sun here in this facility.
Yeah, so the most extreme place in the solar system.
Wow. Time magazine named Kreitzer one of the 100 most influential people in the world in 2023. Now she and her team are working on the next steps for the ultimate goal of clean energy.
We're trying to compress the pellet better. We're trying to hold it together longer so it burns up more of the fuel. We're actually only burning about 7% of the fuel that is in there.
Introducing Zeba, the world's first hands-free sneaker built for comfort. You heard that correct. Zebas are hands-free.
Okay.
What needs to happen to commercialize this source of fusion energy? Since it happens, there's extreme amounts of power. It's like over 30 quadrillion watts, but for a very short time period. So what we would have to do to produce enough fusion energy is have this system be pulsed. It has to be a pulsed system. And we also need to continue to increase the gain out. So right now, the fusion energy that we produced out isn't enough for a working fusion plant. We need to increase that by about another factor of 30.
If we put a lot of resources at this, added many bright minds like yourself to work on it, what might be the earliest that we'd be able to see this commercialized?
If we could move faster and have unlimited resources, it could be within the next 1 to 2 decades.
Wow, fantastic. For her efforts in bringing the future closer, Annie Kreitzer is a 2024 Genius Award recipient.
I think that's good enough there. So, Annie?
All right.
Please come on stage so that we can give you the
Yeah. All right.
Great. Yeah, thanks again so much for having me here. And I'm going to be talking about how fusion could be the future of sustainable energy. A little bit more about the experiments that we did that were kind of what people refer to as the fusion breakthrough, and a little bit on what it's going to take to commercialize that someday in the future. I also was asked to say a little bit about myself and how I got into this field, a little bit about my background first. And I don't know if there's any young people on the call, but I put some of these comments in there to sort of motivate the fact that you don't actually have to come from this culture to be a physicist. So I was the first person in my immediate family to even graduate with a 4-year college degree, and also the first scientist in my family at all. So it wasn't something that I just grew up thinking I would do. I think I found out kind of late too in high school that I love math and problem solving. I knew I always loved that. And so that together with a few key mentors is really what launched me into my career in engineering. And I went to U of M. I really kind of fell into nuclear engineering because they had a scholarship and I had to pay for my own college. And so it was sort of a series of luck and mentors throughout the years getting me here. And then in nuclear engineering, there's a lot of different types of things you could do. I thought fusion was the most interesting, the future of energy. So I also, when I was looking around for summer internships, I came out to Livermore Lab while I was at Michigan, and I saw that's when they were kind of putting together the plans for this NIF laser facility. And I thought that's the biggest laser in the world. So at that point in time is when I decided I wanted to work for for the laser fusion program. And so then I came to Berkeley so that I could do my thesis work out here at the lab because it's about 50 miles drive. And then I just never left. So I stayed as a postdoc, came as a summer student, stayed as a postdoc, and then transitioned to staff scientist. I've been here for 20 years now. And I guess I'm not sure the 18 doesn't count my years as a summer student, I guess. But so I really just was excited about doing science on the biggest laser in the world. 18 years later, I became the first physics designer to achieve controlled fusion ignition in the laboratory, but again, with a lot of people working towards this, huge teams, a lot of mentorship, and a lot of help, and also luck along the way. So, pretty blessed to be where I am and excited about the future. So, as you already heard, the fusion is the process that powers our sun. It is the holy grail of clean energy. We've known about this for a long time, and as you also heard from the video, that we've dreamed about harnessing this energy for quite some time in a controlled way on Earth. And so what we did in 2022 is we demonstrated for the first time in any different type of fusion experiments, there's lots of different ways to try to achieve fusion, that we can control fusion in the laboratory enough that we can generate more energy out and capture that than energy that we put into the experiment. And what we're doing out here at the lab is still a physics understanding experiments. A bigger facility would need to be larger and scaled up. So we're really trying to study these systems, but we did generate more energy out than energy into the experiment. And this was after quite a long time. This concept of how to do this was actually started before I was born in the 1960s and published in the 1970s. And so I'm happy to have, in this point in my career and in history, gotten the chance to work on this. So as you all know, we're in a global energy crisis, not just now because of what our energy sources are doing to our environment, but also because the worldwide energy consumption is projected to increase by a significant fraction, and in not that long of a time from now. So in addition to just trying to reduce the amount of energy sources that harm our environment, we also need more energy sources to supply all of our demands. So currently all of our energies, a large fraction of our energy sources have issues in that they create pollution, long-lived radioactive waste, or create greenhouse gases that impact our environment. And so we need more clean energy solutions to address that and also address the increase in demands. And fusion could be that solution. But we have to start now. We can't wait till the last possible second. So we're working pretty hard at that, continuing to work on that, both in the public and private sectors. So just a quick recap is fusion occurs when two light atoms are smashed together. They create one heavier atom and another particle and release huge amounts of energy in that process. So the types of atoms we're smashing together in our experiments, they're forms of hydrogen, deuterium, and tritium. So it's hydrogen with an extra neutron and hydrogen with two extra neutrons. And you smash them together and that creates helium and a neutron, and that releases quite a bit of energy. That's different from our current nuclear reactors, which take a larger atom and split it apart to release energy.
Hey, Annie, are you showing your videos and stuff yet, or?
That's coming in a little bit.
Oh, okay. Just making sure that.
Can you see these view graphs?
I'm not seeing your presentation.
Okay. I thought I was sharing the view graphs. So
Yeah.
it says I'm screen sharing. I think it's an issue with maybe it's an issue with the recording. I'm not sure my lab allows. Shoot.
Is anybody seeing her?
You mean seeing her screen?
a PowerPoint?
Yeah.
Yes.
Yes.
Oh,
Yes.
Yes, we can see it.
Okay, because I'm not seeing her PowerPoint. Anyway, go ahead.
okay. I'm sorry that you can't see that. I have pictures for everything I'm talking to, so I apologize for that.
Oh, no problem.
So the way that the fusion process releases energy is because the mass of the products after the reaction is slightly less than before the reaction, and that small change in mass is converted into huge amounts of energy from Einstein's equation, E equals mc squared. And that difference in mass is really just because of how the neutrons and protons of the nucleus bind together, and that binding energy is converted into or is released in the process. So the reason why fusion is even more attractive than the other things that were already mentioned is because it's very, very powerful. It has a very high energy density. So 1 pound of fusion fuel is equal to 5,000 barrels of oil, 3.5 million pounds of coal. And compared to our current nuclear reactors, which use the fission process, it's 4 times as powerful as that as well. Just touching on a few more of the reasons why people have been pursuing fusion for so long and why it is the holy grail of clean energy. It doesn't release any carbon emissions. And it also, there's no chance, like our current nuclear reactors, of a meltdown situation. It's so hard to get the two atoms to fuse together that you just turn off the driver and there's no way to have a runaway reaction. Because it's so hard to get the atoms to fuse together, we only ever can have a tiny amount of fuel in the experiment at a given time. So even if you burned up all the fuel around it, it would not create a situation like this. The reason why these situations happen is because it's very easy to split atoms apart, and you have a lot of fuel sitting next to each other because of the way that a fission reactor operates. And that's why it's the safety is centered around keeping that from happening. Whereas in fusion, we're trying the hardest that we can to burn up everything that's there because it's just it's a harder process. The other advantage is that fusion doesn't create long-lived radioactive waste because the products are helium. There is a little bit of radioactivity that happens with the materials surrounding the experiment, but that's very short-lived. And in fission nuclear plants, which is what we have today, the materials that are used in that are they're very, very long-lived radioactive waste and have to be stored very low underground and maintained for centuries. So it creates a whole different problem. The fuel for fusion is unlimited. It's one of the isotopes of hydrogen is found in seawater, that's deuterium. The other isotope of hydrogen can be generated from in the fusion reactor itself can generate it with lithium. So the neutrons that come out of the reaction hit lithium and that creates tritium. And it's estimated that for one person's lifetime supply of energy, the amount of fuel you would need for both of these things is a laptop battery. And I know I have like 10 of those in my house, old laptop batteries. And a bathtub of seawater. So in terms of the whole carbon footprint we're putting on the earth, it's much more attractive. And then of course, this would be, we would like to use this in combination with other clean energy sources. But the advantage to fusion is that it has a very high base load, which means you can run it 24/7. The sun doesn't have to be shining and the wind doesn't have to be blowing. It's a reliable source of clean energy. The reason why it's so challenging to get the fusion process to occur and to control fusion is because of the electrostatic repulsion between the two atoms. So when you're trying to, it's easy to send a neutron in to get something to split apart, and because those reactions don't require a lot of special conditions. But for fusion, you're taking two atoms and you're trying to get them close enough together that the fusion process, the nuclear process takes over, but they have electrostatic repulsion that repulses them away. And it's very hard to overcome that repulsion. So to do that, you actually need to get them going so extremely fast at high temperatures that they have a probability to collide and interact. And those conditions are like the center of the sun. So very extreme conditions. The the types of situations that we're creating in these experiments, they're plasma states, the fourth state of matter. We are actually making miniature stars in our laboratory when we do this. As you can imagine, it's hard to both create those conditions, but it's also hard to hold those conditions together for long enough that you can burn up the fuel. And so that's been the challenge that we've and all the fusion concepts have been struggling with and focusing on. Right now, there's two main approaches to create these fusion plasmas and also to confine them for a long enough time that we can burn up the fusion fuel before you start the experiment over again. The two main ways is with powerful magnets and with inertia, which is called inertial confinement, and that's with really big lasers or also things like pulsed power, extreme electrical current devices can also achieve this. And so there's advantages and disadvantages to all the approaches. So far, the only approach to have ever shown energy gain in a laboratory is laser fusion. But there is growing excitement with significant investment in all of these different areas, both public and private. So the approach I'm talking about today, you already saw it in the video. It uses the biggest laser in the world, and here's a picture of the building that you saw in the video. It's the size of 3 football fields. Most of this building is the laser beam lines. So because this laser has older laser architecture, this laser was built quite a long time ago now. New lasers can be much smaller than this, but it is still a very, very impressive machine. So in this building over here on the right side, about this big, sits what we call a target chamber, which is a metal sphere. And I'm going to be showing that on the next slide. It's also the photo behind me. And I'm not in the NIF facility right now. I think they're getting ready for a shot. I'm in my office. But this is the same picture as what you're seeing behind me. This is the blue sphere here. You're looking at the top of it. So it's actually separated by many floors because it spans multiple floors of a building. It's about 10 meters in diameter, about the size of half of a tennis court. That's this blue sphere. Inside of the laser beams enter into the blue sphere in these holes, which we call laser ports, and you can see some of the lasers coming in here. And inside of the chamber, the blue sphere, sits a 1 centimeter long hollow can made up of a high atomic number material. So a metal, here it's gold line depleted uranium. For fusion power plants, we're looking at other cheaper materials like lead, and possibly other materials like copper. Inside of that can sits a little capsule. It's a hollow capsule or sphere. And inside of that sphere is where the two isotopes of hydrogen are fueled. So the fusion fuel sits inside of there. And that little sphere sits in the middle of the can. We squeeze and compress the BB size or peppercorn sized sphere down to half the width of a human hair. And that's how we make our tiny miniature stars in the lab. And a fusion power plant would scale this bigger. So there'd still be very miniature stars, but bigger than half the width of a hair, maybe the full width of a human hair. And to put this in perspective, it's like we're trying to take something that's the size of a basketball and we're trying to squeeze it down to the size of a pea. So as you're squeezing and compressing the material, it heats up and you're transferring the kinetic energy of the squeezing and the change in volume. You're converting that to heating and compressing of the fuel, and that's how you get these sun-like conditions. So the way that we actually do this is by hitting the lasers onto the can, not directly onto the pellet. If you hit the lasers onto this metal can, it creates an X-ray oven that's 3 million degrees. That X-ray oven, it heats up the outside of the capsule material, and that capsule material explodes out, and that squeezes the fuel down to a very small volume. And once you can get the fusion fuel to, we call ignite, then we try to burn up the rest of the fuel that's in the pellet as much as we can. And that's what we're focusing on right now because we've now gotten it to ignite very routinely. But we haven't burned up all the fuel in the capsule. So we're trying to figure out how to change the physics parameters even more to get more fuel to burn. And I like to use the analogy, it's kind of like you have a match and you have all the fuel for continued burn in your match, and you're just trying to get it to ignite so that you can sit there and burn up the rest of the fuel in your match. But if you don't rub it hard enough, you may not get it to ignite in the first place. And that's where we were for quite a long time. So this is another video. It's similar to parts of the one that you saw before, but I'm just going to do a quick voiceover on the video. So our control room is modeled after NASA, that we have stations for all the different components. The laser beam lines span the 3 football fields. It comes into the target chamber, 192 individual beam lines, comes in as red light. We convert that to blue light. That blue light enters the can. It hits the inside of the can, and that creates the 3 million degree X-ray oven. So X-rays are coming in. A main challenge is making the X-ray drive be spherically symmetric, because if you can't squeeze that down just right, it won't ignite. And then once you do get ignition, it's a very rapid increase in temperature. It's a very fast process, and then you burn the fuel and it explodes, and the whole experiment is over. So a fusion power plant would actually take these targets and send them into the target chamber one after another and hit them and have them ignite and produce energy in a pulsed methodology. So let me go to the next slide. This is a zoom in of the target that we saw in the previous video. And the difference, the main thing that we did in 2022 was we produced more energy from the fusion process than laser energy into the target. And since that experiment, we've further increased the amount of fusion that we got out. So I said that's what we're working on, and we have made progress kind of at another factor of 2 level. So the first experiment got 50% more energy out than in, and now we're at more than 2 times energy out than in. And what we're doing here is really the physics that we're studying at this small scale. It only will get easier as we scale things up in the future for a fusion power plant. A lot of other areas of active research include the laser itself. I mentioned this is old laser architecture, and it's a very inefficient laser. So getting the energy into the target to begin with is an inefficient process the way we do it here in Livermore. But we just wanted to be able to get the energy in so we could study the physics. Meanwhile, people have been developing lasers for decades. So the lasers we know we can build now are much, much more efficient. And the ultimate goal is you get more fusion energy out, including all the losses along the way, even the laser efficiency, so that you get more fusion energy out than what you pull from the wall plug in total to even power the building, to power the laser. So my role in these experiments, I think you heard it in the video, was to try to adjust. There's there's hundreds to thousands of little parameters you can adjust about exactly how this target looks like and exactly what we do to the laser, how we define the laser energy coming in to be able to create these conditions. And those are our free parameters. So when we have the same laser system and we're trying to improve things, it's by making changes to these things and trying to get just the right plasma conditions. One thing I mentioned was if you can't squeeze it down just right, you might not get it to ignite. You kind of get a dot or a fizzle. This is an example of that where it's like taking a basketball, squeezing it down to the size of a pea, and if you can't control that to a percent level, then it squishes out in one direction. That's this. This is an actual neutron picture of what it looks like when it's trying to ignite. This is data. And then this is adjusting the laser parameters just a little bit. We got it to more spherically compress, and this one did ignite and took off. So that's we're using very highly developed, complex computer simulation tools to do that, which have also been developed over decades. So really cool tools here at the lab to tackle these very complex physics problems. And the path to commercialization of fusion is no longer sci-fi. There is still quite a ways to go, but now that we've ignited the plasma, that was sort of the question was, is there something fundamentally keeping us from igniting a fusion plasma in a controlled laboratory environment? And now we've answered that to be no. It actually helps a lot of the different fusion approaches figure out how far away they are and maybe how to improve. And also you can see that once you've ignited the plasma, then 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 burning up the fuel helps you achieve higher and higher gains much more quickly. So that's what this is showing on the right side. This is fusion gain, so energy out versus laser energy into the target. This is each bar here was an experiment that we've tried. This is number of experiments, but this spans over a decade of work, actually more than a decade. And down here, there are bars, but they're so low you can't see them on the plot. You can sort of see little cyan here. This was the first actual scientific ignition experiment in 2021. And this was the first target gain experiment in 2022. And this is the progress we've made since then. But as you can see, this period here was less than 5 years. So once you start to make progress, you can start increasing gains very rapidly. We still need in a bigger system to be able to get gains that are higher than what we have now. We think the bigger system will help with that, but we also, the more improvements that we can make now, the better it is for a bigger system. So in terms of how to commercialize this, we need higher gains. We need more fusion energy out for a given laser energy in. We need lasers that can do these experiments at a faster pace. We only do a handful of these a year for various reasons. But these lasers exist and people have been working on these for decades. We need to build bigger lasers and have them be more efficient and have the targets be cheaper because right now they're kind of boutique targets that are made for every specific experiment individually and they are hand assembled and it's really kind of still just a physics not a streamlined production mentality for the targets. And the tritium supply is basically how do we generate the isotope of hydrogen that you have to do from a reaction on lithium? How do we do that and recover it back into the system so that we can continue to operate and self-generate this tritium? And with that, I will leave it on our cool ignition meme, and then I'll take any questions.
Thank you so very much. Um, yeah, my video is messed up for some reason. But
Oh.
thank you so very much. And this was really, really good, very insightful into this future source of energy. I think you said maybe in a decade or two. And so I have a number of questions, but
Hmm.
I'll defer to my co-host to see if she has any comments, questions, and so on.
Well, no questions, but I do want to thank you, Dr. Kreitcher, for your insights, your expertise, and your vision. Thank you for sharing that with us today.
You're
I
welcome.
know that I'm grateful, as well as Dr. Murray, for your time, your wisdom, and the inspiration you provided to our guests today.
Hmm. So my first question is, how do you convert red light into blue light?
There is I wonder if I can stop the video here. I guess you can't see it, but there are crystals
Okay.
that convert it basically it's like when you have a crystal and you see it can spread the light apart.
Okay.
It's just like that. It's a very fancy, very it's one of the seven, they call it a seven wonders of NIF because the crystals they had to make for to do this for this big of a laser were so perfect and so large that they had to develop new ways of growing these crystals. But it's the same idea as you just spread the light apart and you can pick your color.
Okay, so this is not just limited to red to blue. You could do other color conversions.
Yeah, and we say red and blue to make it simple, but it's really converting to the from the IR to the ultraviolet. So it's actually not visible here, but we're just kind of using that to
Okay.
show, yeah.
Okay.
But yeah. Hmm. The wavelength, the laser wavelength you want on your target, that's one of the physics design parameters, and the reasons for that is because as you as your laser comes into the can, the wavelength changes how that light interacts with the metal material and how it's expanding out into your can. So it's more favorable to have a very specific laser wavelength.
So the other question has to do with into the future. So obviously this is high tech. There has to be some really, fundamental, um, you know, s- infrastructure, personnel, and all of that to operate systems of this nature. How do you foresee? So I'm assuming, for example, like in developed countries, they would have those types of resources. But how do you see this being applied to, I hate the word, but I'll still use it, underdeveloped?
Hmm. I think the energy can be, I think there would have to be a lot of government influence, a cooperation to help transfer these technologies to other countries. Um, I think I stay out of the political side a little bit, so I'm more focused on just the physics, but I think transferring these technologies to other countries is essential. It's something that I think everybody wants to see. I think just thinking about it a little bit naively is, you can also give energy without having to transfer the technology fully.
Yeah.
So making energy available to all equally, I think that's the grandest human vision that we have, and I think that is where we hope to get to.
Hmm.
The exact way that it happens, I actually I have thoughts, but I don't know.
Yes, yes. Because I'm thinking about like I'm from, the Caribbean,
Hmm.
and you were talking about the seawater and stuff.
Yeah.
And so many island nations around the world has that resource available.
Hmm.
I'm just kind of thinking, how would they be able to utilize that resource?
Yeah.
Yeah.
I think we can take a lot of cues from the fission industry, from the nuclear industry we already have, and how they may have translated these technologies and trained workers in different countries to learn. So some sort of apprenticeship training program and transfer of technology between governments.
Mhm, mhm.
Countries.
So we open up the floor, if you will, for comments and questions.
Dr. Murray?
Go ahead.
Well, I want to thank both of the women for educating and inspiring us through the works that they're doing. I cannot wait to get this book that's coming out by your host and hear more about her. And then I want to focus on the speaker. She was phenomenal. I'll be quite frank. I thought, will I be able to understand all of this as a non-scientist? And I really appreciated how she simplify things so we could understand. Because for most common folk, we're looking at our electric bills going up, energy crisis, we're hearing things in media, and it's just really making us wonder, where are we going for in the future? And just hearing what they're doing, it gives us hope for the future. That there are dedicated and skillful people like herself and her team that are really striving to make our future better. And I'm glad I tuned in. I thought, well, energy, how much of this will I know? But I left out again, knowing more than when I tuned in at the beginning. And I just love her deliverance. I would love for her to even come back I could just see her going into classrooms, because our world that we're living in today is leaving us wondering about energy and how will the future of energy. I'll just phrase it that way, the future of energy. And again, I'll just repeat, I'm so glad she's doing what she's doing. One more thing, I love her intro, her bio, talking about just her everyday family life, how she was the first one to look into this career and her other family members were doing other things. For me, that gives students and parents hope. I'm an auntie, I don't have children, but it's hope that our children will be inspired by what she's doing, when she was the first person in her family to go into the field that she's in. And so I loved it from the beginning to the end. Bravo. Thank you, and Dr. Murray, thank you for having them here with us today.
Okay, Laurel.
Yes, thank you so much. And I can't think of a better time than now to be learning about more greener energy alternatives.
Yep.
And our reliance on foreign non-renewable resources is catastrophic. And I think this could lead to, at some level, world peace. I'm trying to be very positive in a very
yes.
So thank you so much.
Yes. So yeah, I think Princella touched on something that I noted very early, because one of the initiatives that I have is called early research. And I see that in our speaker that she started doing research early. So could you tell us a little bit more about what was the earliest time that you actually got into a lab and started doing research? High school, college, what was?
Yeah. It was actually undergraduate college. So in high school, I loved math,
Mhm.
calculus, but I wasn't actually hands-on in a lab.
Okay.
I think when I went to be an undergrad as an engineer, I first started out kind of in the civil engineering area, and we were hands-on. Actually, the first project was to build a concrete canoe and have it float. That was really cool. But my first experience in a real laboratory was in a radiation safety and detection laboratory as an undergraduate at the U of M. So
How did you
yeah.
make a concrete canoe float?
A lot of great civil engineering past work, basically, in following the textbook.
Okay.
The shape, and it's all about the shape. So,
Oh, okay.
yeah.
All right. Pat from Trinidad.
Yes, so coming from a country that is economy is based on oil and gas, and as a sort of environmentalist, being horrified at this, but trying to imagine this. How would you, once you have this energy, how would you transport it? If you, I really think that it would be a long time before small Caribbean islands, for instance, would be able to access this sort of technology. But I'm thinking about, once you have this, how would it be transported? Would it be along kind of normal, like electricity or
Yeah, exactly. So the way that there's different ways you can use the energy from these reactions, but one of the main ways is to take the neutron energy coming out, and boil water with a steam turbine and then convert that to electrical energy. So that is the way that our current nuclear reactors generate electricity. So that's how it would be done here as well.
Okay. Laurel, you have your hand up still. You have another comment or question?
No, I'm on my phone, and so I probably just didn't find the little control to put it down.
Okay, no problem. No problem. And Pat, did you have a follow-up?
no, not at this point in time. Did I leave mine up too? I
Oh,
thought they
no.
said that it would come down.
Yeah,
No,
it's down. I was just wondering if you had
right. No, but I mean, because at the present moment, our alternative seems to be hydrogen,
right.
and that is the way that they seem to be going, rather than, I mean, you're absolutely correct when you say that wind energy and solar power are very much dependent on conditions. And so, but hydrogen is a bit scary, although it goes throughout, it's being used now more and more throughout the world. But this sounds as if it could well be a safe method of producing electricity. And I think that is the key here. And thank you so much. But it sounds as if this recording is not going to be available. Is that correct?
It will be. It will be.
Okay, no, because I think I would like to be able to pass it over to some people, give them food for thought. Thank you very much indeed.
Yes. So, since your discovery, that was in 2022?
That's correct. Yeah.
Because the way science works is that, once there's a discovery, a lot of people then start to build on it. Are there other groups? Again, you work at a national laboratory that has lots of resources, but are other groups now using and building on what you have discovered?
Yeah. So there are private companies that
Okay.
are trying to use this information. The reason you haven't heard about big results in the news is because it takes many years to build up a new facility to get the results. But they are using the physics information to motivate their companies. So there's a few that actually four or five that are very well tied to this scheme, and they're getting private funding to pursue that, and we'll be building facilities in the future. There's also other countries you may have heard about in the news that China's also building a bigger laser system. So
Okay. So, without, drawing you into like the current politics and stuff, um, is your national laboratory affected in funding or personnel, um, under our current, situation?
we are impacted a little bit, but because we are government contractors and most of us are not federal employees directly,
Oh.
it's not as impacted currently as what you're hearing in the news,
Right.
but we are, and beyond that, I'm not sure what I'm allowed or what I should be saying on behalf of the laboratory, but
Understand?
yeah.
We understand. There are people on here that very much understands what you're talking about. So okay, so as far as things are going, for the most part, you and others will be able to continue working in this field and developing and building it.
Yes, we're continuing to do experiments. The experiments because of the cost, because of the way the laser is designed, and because we use the laser for for other experiments. We don't do these shots very often. We don't do these experiments very often, but we continue at the same pace that we have been.
Mhm. Okay. All right. Are there comments or questions? Mary Alice?
Good morning, everyone. Thank you, Dr. Murray. To Azrina, you say you're government contracted. Can you give a little more information about how that works in this type of work when it comes to funding? Are you allowed to sub out work or what? How does that work? Working
Well,
with an organization that's interested in this.
oh, can you repeat the last part of that? You want to know how, as a government contractor, we can work with other companies?
Not so much as companies but organizations that are interested in obtaining this technology
Hmm.
in my community as a nonprofit. How does that work? If I'm looking for your services that you provide, do you actually sub out some of that work to another contractor, or how does that work when it comes to funding with a
Um,
nonprofit organization?
yeah, so let's see. Right now there's ways for the national labs to interact with organizations. They're like licensing or contracting. We are nonprofit because we are taxpayer dollars, so everything we do is open to everybody. Right now, there's, it's not like we can just take this, what we have right now, and come to your community with clean energy. So quite a bit of work has to get done still for that to happen. If that's all done within the national laboratory setting, I think it would come through the government to the communities. If it happens through a private company, so that these private companies are coming up with funding, they can move faster than the government if they get to the point for commercialized fusion energy before the government, which isn't actually focusing on that, we're focusing on the science. Then that would be a normal kind of company situation. And the way the lab interacts with the companies is it licenses technology so that some of that benefit comes back to the taxpayers through that mechanism. But in terms of like how do you get this technology to your community, I think that remains to be seen at this point because the technology isn't fully ready.
Develop. Okay, so even if that's the case, like a lady in waiting,
Hmm.
does that mean that a policy within a local municipality or a unit, village, or what have you, has to be in place to be able to submit or request such thing? To,
Yeah, that
okay.
I think I see where, yeah, so the local, yes, there's got to be a lot of policy work to be done to get these new
Ordinance.
technologies. I
Okay.
think there's people working on that like as their sole job. There's a lot of people working in those angles in both from the community side and from the government side. That's not my active area, so I'm not sure what I know there's progress being made in public policy for fusion, but I'm not sure exactly where it stands and how close it is. I think by the time we get fusion ready to be plugged into the grid, I'm hoping that the policy piece will have matured. But there is the whole like getting the whole community familiar and with fusion and comfortable with it. And that's something that people are coming at from all angles. And I was just at a conference with a young lady who's educating grade schoolers on a routine basis on fusion energy to make it commonplace and to get more people into the field, and to get the community really comfortable with it. So I think it is going to take a lot of people.
So, in terms of the science, I know you listed like maybe five, six, seven things, but of all of those, what do you think is the most sought after next development? What is, the top one or two things that
Mhm.
would push this science, technology, and all that, further?
So I think the thing is if we can get hired gains, if we can change the parameters so we can get more fusion energy out for a given amount of energy in, that's one of the biggest ones. The other one is the components that go into these targets, making them cheaper, simpler, and manufacturable. And because you're shooting these over and over and over again, you can't have them looking like this target here, which is highly specialized in boutique targets. And so we have people working on different materials that go in here, and also in trying to see if these are manufacturable or generate systems where they can be manufacturable.
Okay. All right. Very good. So, are there other comments or questions? All right. If not,
If I may. So do you suggest that this is something that we start working on now? I mean, I don't know what it would look like with the state as a whole, because I'm sure it has to start at a state level as opposed to, I mean, the state and then it trickles down with
Mm-hmm.
policy and law. And okay.
Yeah, I think the sooner we can start working on it, the better, because there are other fusion schemes that are um, starting to build immediately. And if you build a bigger laser immediately to answer to address some of these questions, you'll run into the same policy restrictions, and it is state by state. So that's why there is one fusion scheme is putting their reactor in a specific state for that reason. So getting all kind of states up to familiarity in the policy to be friendly towards fusion, I think now is the right time for that.
Fusion friendly. That's a good word.
Yeah.
Fusion friendly. Okay, so we have an election this year, and as a legislative chair for almost 12 years, um, I know how long policies and stuff can take to put into place. So it's if an idea comes up that benefits us all overall, especially when it comes to cost savings of customers,
Hmm.
and we need to be working diligently at getting things done instead of meeting just to be meeting.
Hmm.
Yeah. Thank you, dear.
Thank you.
all right. Well, we want to again thank you so very much, Annie, Dr. Kutcher. We want to also thank our co-host today, Dr. Elissa Gabrielle. Want to thank our regular viewers, audience, and everyone else that's been on here today. We hope that you all have a great weekend. I know I learned a lot, and we'll be looking forward to developments coming from your work. Thank you so very
Okay.
much, Dr. Kutcher.
Thank you so much for having me.
All
Thank
right.
you.
Thank you very much indeed.
Okay.
Take
Bye.
care. Bye bye.